I will talk about PhD observations of gamma ray bursts. And so LAPP displays it's a laboratory of particle physics. So there's a lot of collaboration with experiments at CERN, such as Atlas and CMS and so on. But there's also a big group of physicists doing instrumentation and data analysis on gravitational waves with Virgo. And then also this group that is doing astrophysics with Cherenkov telescopes. So you will see the type of things that we do in this laboratory in the following slides. And so starting, I will start with the basics. One thing is what is the definition of PhD? And what we're talking about is observations of gamma rays in the range of 100 giga-electron volts up to 100 tera-electron volts. So this is like the highest energy or the highest end of the spectral component that you can see in gamma ray bursts so far. So we are talking about extreme particle acceleration. And then there's a lot of link between this type of objects and particle acceleration itself in laboratories that we have at ground. So this is the content of the talk. What I will do is give a brief introduction, very general, to what are gamma ray bursts, and sort of trying to introduce as well the problems or limitations that we have for observing these objects at very high energies. Then I will talk about the instruments that we use to detect them. So these Cherenkov telescopes and also wide field instruments. And then I will go through the detections that we have so far. So essentially, the problem was that GRBs were detected in the 60s, and we started to learn a lot of them based on observations by satellites. But since the 60s up to a couple of years ago, there was no detections at very high energies. And I mean, it's already suggesting the fact that we're talking about gamma ray bursts, so they are extremely energetic, so you would sort of naturally expect that they can emit very high energy photons. And it was very intriguing the fact that there was no detection for roughly 15 years that this type of instruments that I will talk about have been functioning. So all of a sudden we got detections, and then we started to understand more about these environments of gamma ray bursts and why it can emit at very high energies. Well, in the end, just to sort of finish up, I will talk about future instruments. So what are the developments in terms of instrumentation and studies looking forward to improve what we know already from gamma ray bursts. So gamma ray bursts have these two scenarios. One is the emergent scenario in which we have compact objects such as neutron stars orbiting and then merge into one single object that eventually will give rise to something that we call the central engine that we don't know very well what it is. The other scenario is this massive hypernova scenario. We have a massive star of the order of 30 solar masses, a bit more, a bit less, undergoes gravitational collapse and again gives rise to the central engine. What happens here is that this central engine will start to rotate, form magnetic fields, and it will give rise to these jets in which particle matter will be released in these sort of blobs. And the idea of these blobs is that it's just matter being released at relativistic speeds. Eventually, because they have different velocities, they will collide with each other, and we will call this an internal shock wave. Inside this internal shock wave is essentially just a discontinuity in terms of matter and velocity. I mean, it's exactly the place that you need to generate particle acceleration. And the mostly accepted scenario for emission of photons that we see in gamma ray bursts is synchrotron of electrons that are being accelerated in these shock waves. So this will give rise to very distinct phase in the gamma ray burst, which is the prompt emission. So what we are plotting here is the flux as a function of time. So we call this a light curve. And the prompt emission is characterized by a very chaotic sort of peaks, random, very fast variability, which is essentially just different blobs colliding with each other, accelerating particles and emitting. And one thing that we can observe from the prompt emission phase is essentially the duration that we call T90, which is the time interval in which 90% of the emission is seen. And you see a bimodality in the distribution of this duration, in which we identify short GRBs with duration of smaller than 2 seconds, so the duration of this prompt emission phase. And we have seen a relation between short GRBs and this merger scenario, while long GRBs with durations bigger than 2 seconds come from this hypernova scenario. So after the prompt emission phase ends, then it comes the afterglow. And it's basically the consequence of this ejecta reaching the outer environment. So the ejecta starts to slow down and eventually finds the circumverse environment, which is just all the dust that is surrounding the central engine. This will give again rise to a shock wave, which we call external shock wave. And this shock wave will also have a reverse shock wave that then we can see, for example, in radio. But the important thing is that naturally, I mean, there's no more chaotic thing going on. It's just this thing propagating to the outer part. And we see the signature of this phase called the afterglow as a power law temporal decay, so roughly T to the -1. So it's very fast decaying. And we see this in almost any wavelength. One thing that is very illustrative, yes?
At least what the scenario you were showing, that's for both short and long.
The afterglow, we see it in both type of scenarios.
And diagram also is the
So
scenario
this,
for the
for
the central engine.
exactly, yeah. So the thing is, this is different. The afterglow is very similar for both scenarios. And this essentially tells you that the outer environment is just the same. It's just dust and this jetted emission punching so to the outer environment. Yeah. So one way to illustrate or explain, I mean, I like this explanation very much to understand why GRBs are jetted. And this is called the compacity problem. So what you have is, so we see a lot of X-rays in the prompt emission phase. It means that there's the possibility of, I mean, there's a lot of photons, but these photons have also the possibility of creating pairs. And this is the condition for the production of pairs. If from a source you see a lot of photons, it means that by definition it's an optically thin environment. And the condition for optically thin is to have this expression of the optical depth smaller than 1. But if you plug standard values of this into what we see from gamma ray bursts, so variabilities of the order of 10 milliseconds, then you get to optical depths of the order of 10 to the 15, which is very big. I mean, way bigger than 1 for sure. And so you arrive to a contradiction. It means that X-ray shouldn't escape from these environments because you are not reaching the condition of optically thin. The thing to fix it or to alleviate it is to introduce a Borg-Lorentz factor into the expression that then makes your condition of optical depth sort of applicable. And what you need is Borg-Lorentz factors of the order of 10 to 1000 for this condition to apply. Another way to see this thing is that the MEV photons that we see from gamma ray bursts are actually kilo electron volt photons in the source. So we observe them because they are jetted. And kilo electron volt photons don't undergo pair production. So that's the part to sort of understand why this is a jetted emission. And also there is a characteristic thing that we sometimes observe in gamma ray bursts. Light curves, which is the jet break. So in the afterglow, you see a temporal decay that is very smooth, but eventually it becomes steeper. And that corresponds to the point where the beam emission starts to slow down, the jetted angle starts to open, and at some point it becomes fully observable to Earth. So it's when so it becomes fully observable to Earth, and eventually it starts to be less observable. So there's a lot of emission that you don't see anymore because it's escaping the observer. Another characteristic of gamma ray bursts is their extragalactic origin, and this is very important to consider for the observations at very high energies. So if you see the distribution of redshift for GRBs, it's rather uncommon to have a redshift. Roughly 30% of the GRBs do have one redshift, a redshift measurement. And it essentially picks a roughly 1. It depends a bit on the classification if it's a short GRB or long GRB, but more or less it's 1, maybe 2 or something like this. The problem with the VHE emission part, so GBTV photons, is the extragalactic background light. And essentially, well, you might know what EBL is. It's all these photons that have been released in the epoch of recombination. They're just floating, and they serve as a sort of an attenuator for the VHE photons that are emitted from the sensor. So the condition is more or less like this. If you have a 1 TeV photon, then you will produce, I mean, 1 photon of the EBL with 1 photon of your source will undergo pair production. And we're talking about EBL photons of the order of 1 electron volt. So it's optical EBL photons, infrared or ultraviolet.
Sorry, Edna, what do you mean by EBL photons?
Extragalactic background light. So like the photon fields of the extragalactic background light.
Oh, okay.
So this ends up with some sort of absorption of your emitted photons from your gamma ray burst. The more distant the GRB is, the more absorption it will undergo, because I mean more field to travel, more EBL, more chances that this condition will happen, and then pair production will occur. And so, as an example, for a GRB at a redshift of 0.1 and an energy of say 1 per electron volt, you can see that sort of 60–70% of your flux remains unabsorbed, so 40% of your flux is absorbed. And if you go to 1 to 10 electron volts, you are only receiving 0.02 of the original flux that was released from the GRB. And then this becomes even worse when you are talking about redshift of 3. So essentially, what this tells you is that if there's a GRB at a redshift of 3, that there are a lot of GRBs happening there, it's super difficult to detect them at very high energy because they will not arrive to Earth. To continue going through the story of VHE detections, I will talk about the sort of historical GRB, which is GRB 130427A. So the naming convention for GRBs is the first 2 digits is the year, and then the month and the day, and then you assign ABC in the order of the day. So this GRB was detected in 2015 by Fermilab. What Fermilab saw was a lot of energetic photons. So what we're plotting here is the energy as a function of time. Each dot is one of the photons that Fermilab detected. And the maximum energy photon seen in this gamma reverse is a 98 electron volt photon at roughly 200 seconds after the beginning of the burst. There is some sort of debate on what is the origin or what is the emission mechanism that can give rise to GRB photons in gamma ray bursts. And there is a theoretical limitation, which is called the Burnout limit. This is essentially the fact that electrons, I mean, you can accelerate electrons, but then they will eventually would like to release this energy in the form of synchrotron. So you arrive to this condition when you equate the acceleration time of electrons and the cooling time to the synchrotron. And with this condition, which is essentially some factors, and this Wolf-Lorentz factor as a function of time, that then this is a function that you can modify assuming different ejecta dynamics. You end up with these lines. So anything that is above these lines is violating this Burnout limit due to synchrotron, and meaning there should be some other, I mean, either the assumption of the Burnout limit is wrong, or there should be some new emission mechanism that can give rise to photons violating this condition. So remarkably, this 98 electron volt photon can violate even the more optimistic scenarios for the ejecta dynamics, and even later times, like several. This is probably 2 or 3 days after the beginning of the prompt emission phase. It's also violating this Burnout limit. So the idea is to at VHE energies is to try to understand if indeed the Burnout limit is being violated and if there exists an additional spectral component at very high energy. So the picture is like this. You have synchrotron that we know very well that can explain the emission at radio optical X-ray and to emitting gamma rays. But then at GeV, TeV energy, things start to become obscure. And one of the most accepted scenarios is synchrotron self-compton. This is essentially, you have your electrons being accelerated in magnetic fields, emitting photons, and then this same population of electrons and photons will do inverse Compton scattering to produce even more energetic photons. So that way you can reach, you can explain emission of photons in the synchrotron, and then with these same photons boost them in order to reach GeV energies. So what we do is to use satellites to observe GRBs in this regime, and then very high energy instruments to cover this interval. I will talk about some of the findings of these instruments and then some also things in the future. To understand also why GRBs are difficult at very high energies, these are some relevant numbers. So these are the energy ranges in which Fermi, GBM, LAPP, and SWIFT are operating. So this is essentially X-ray photons, and these are low energy gamma. And the occurrences in X-rays, so what SWIFT and Fermi are capable of detecting is roughly 1 GRB per day. So 1 GRB per once per day, we receive an alert of this type of satellite saying there's a GRB happening in this direction in the sky. It's becomes more common to see high energy photons from GRB. So, for example, the detection of 130427A was rather uncommon. This type of observations happen once per month. And then the story is that at very high energy, there were zero GRBs in more than 10 years before 2018 when we started to do the detection. So, talking about these GBTV instruments, this is sort of a map of where things are now. We have ICT instruments, imagine atmospheric Cherenkov telescopes, located in the United States, Veritas. Then we have also MAGIC and LSC in La Palma and CRES in Namibia. And then we have wide field instruments like HAWK here in Mexico and LASSO that is in China. So now I will talk about the principle of operation of the Cherenkov telescopes. So the idea here is that you have gamma coming from an astrophysical source, can be galactic center, a gamma ray burst, an LDM, and it reaches the top of the atmosphere, and in the top of the atmosphere, it collides with an atmospheric nucleus, and then it generates this extensive air shower. So the extensive air shower will carry like the particles that are sort of initiated by the collision of your primary gamma or cosmic ray in the atmosphere. And the ICTs will observe the Cherenkov radiation that these particles emit when they are traveling in the atmosphere. So this is a photo of the biggest telescope in the head side, and there's a person here for scale so that you give yourself an idea of how big these instruments are. So essentially, we have this mirror, and then here we have photomultiplier tubes that detect the Cherenkov light being emitted in the atmosphere. What we have are two different types of atmospheric showers. One is gamma ray showers that are what we're interested in studying, and we have background that corresponds to cosmic rays, so protons, electrons as well, helium, iron, and so on. So one way to distinguish both and reject this as our background is by looking at the distribution of the atmospheric shower. So essentially, a gamma ray will create a very symmetric and very uniform atmospheric shower, while cosmic rays tend to undergo, for example, pion decay, producing muons and heavier particles that will generate a lot of asymmetries in the profile of the shower. So you can see here, for example, an example of a 0.3 TeV gamma ray compared to a 1 TeV proton that you see here. Probably there was a pion here producing muons and then generating asymmetries in the cascade. So the idea here is that with the telescope's viewpoints, you detect the Cherenkov light emitted by the secondary particles. And in the cameras, what you see is this type of ellipses. And we actually do a very simple fitting of these ellipses in order to do a first guesstimate on the energy and the direction of the primary particle, and also to perform rejection of cosmic ray showers, because a cosmic ray might not be well behaved with this sort of ellipsoidal assumption. So broadly speaking is the way that these type of instruments function. Of course, now there's a lot of sophistication with machine learning stuff and Monte Carlo templates, whatever. You can ask me later if you want to know more about it. And in the case of GRBs, the story is sort of a bit more complicated than just pointing towards a direction, because we don't know when a GRB is going to happen. So this is just an illustration of how standard Cherenkov telescope GRB program works. This is very related to HESS because I was working in HESS before, but it works with almost any other ICT currently now. So the field of view is rather limited. We cannot observe the whole instantaneous sky at the same time. And then we have this capability of being in any target within 100 seconds. So if you tell me to point my telescope towards this direction, I can be within 100 seconds. And then there's this energy threshold at 100 gigaelectron volts, but it's also semi-dangle dependent. So the higher the semi-dangle, the higher the energy threshold is. And then there's the limitation of VBL, because at higher energy, VBL is worse. So the better, it's better to have GRBs and other sources with well localization in the sky. So what we do is we have something that is called the General Coordination Network, which is essentially a set of machines that what they do is they distribute alerts from this type of observatories, so SWIFT, Fermi, but we also have streams for gravitational wave detections and neutrinos. And all these observatories process the data in real time and send alerts if they see something interesting. So these alerts are being listened by our telescopes, and we have some criteria in order to decide if we want to follow up on this type of alerts or not. Because, there's limited observation time. ICTs can only observe during night, and there are also some other science cases that we want to cover. We want to observe the galactic plane. We want to observe probably a neutrino instead of a GRB, because it might be more interesting. So we need to do some sort of compromise, trying to observe only the most promising GRBs. And with all these things, what you get is roughly 10 GRBs observed per year for ICTs. This is a sort of illustration of what kind of things can happen. It can be sometimes, so in red are GRBs that are directly observable in the night. So we are observing, the Crab Nebula. We get an alert, and then we point instantaneously to one of these alerts. And there's also the possibility of a GRB happening when there's light. The sun is out, so we have to wait a couple of hours or probably a day or so on to observe them, which will be the case of these later observations. So all in all, there's a big limitation, because also there's a latency in the time that these satellites send the notices. And so, for instance, Fermi takes roughly 30 seconds to release an alert, because they need to analyze the data, decide if it's or not a GRB, and if we want to send the alert to the other community. So that means that GRBs are hard to detect at very high energies. I already explained the fact of the event absorption, then the fact that there's a rapid decay in the flux. So if we're talking about these 30 seconds that Swift or Fermi takes to issue an alert, we're already in the afterglow phase, meaning that for ICTs it's basically impossible to detect the prompt emission. And then all these instrument limitations. There's a limited field of view. We cannot observe when there's moonlight or when there's the lights, and the notice time, latency, and also limited observation time because we want to spend time in some other science cases. So then it comes the complementary of these other type of instruments, which are the wide field instruments. So we are talking about instruments that are capable of observing almost the entire instantaneous sky, and there's no limitation because of moonlight or daylight. And the only probably unfavorable thing is the sensitivity. So these sensitivity curves mean that any astrophysical source whose emission is above these lines will be detectable at the level of 5 sigma. What you see here is, for example, the sensitivity curve of Hawk with an integration range from 1 to 5 years. So it means Hawk operates for 5 years trying to observe a source. It reaches the sensitivity. And this is comparable to observations or exposures of Cherenkov telescopes such as HESS, CTA, and so on at 50 hours. So, I mean, what I'm trying to say is that they are very good because they have this wide field capability, but the sensitivity is way lower. So it's these two things coming into play. So the way these things work are slightly different. So we still have our atmospheric shower, but instead of pointing our telescopes and getting the Cherenkov light from the atmosphere, we detect the footprints that this shower leaves in the ground. So what we have is a lot of water Cherenkov units. So it's essentially tanks with a lot of water inside, and then photomultiplier tubes at the bottom to detect the Cherenkov radiation that these secondary particles leave when they enter the water. What you see here is an event of a gamma ray overplotted on the array itself of Hawk, and the color corresponds to the time profile of this shower for the secondary particles arriving. So you see that there's a gradient like this. And what we do to obtain the direction of the primary gamma ray is just you take the perpendicular of this plane, and then the perpendicular will point then to the direction of the primary gamma ray. And to estimate the energy is essentially the more tanks that are lighted and the intensity of the light that each tank receives is very well related and almost 1-to-1 to the energy of the primary gamma ray. So we have Hawk and LASSO doing this type of observations, but as a spoiler sort of thing, we don't have anything in the southern hemisphere. So there's also a big project trying to build some type of instrument in the south to complement the observation of Hawk and LASSO. So this is now the GRB detections of.
How do the satellites go?
The satellites, it depends. So, for example, Swift has something that is called a coded mask. A super fancy thing. It's essentially you have like a weird pattern, like honeybee patterns, one in each other, with different patterns both. You collect X-rays with focusing sort of optical, optical focusing lenses, but for X-rays, which look like a conical thing. And what you do is, so you can think about it like, so you do this pattern like this, and if you light this pattern from this side, at the bottom you will see a different figure than if you light it from this side. And that's the way that you can pinpoint to the direction. The energy, I don't know. And the other one is Swift.
So in that case, it's directly to the no secondary.
Yeah, exactly, it's directly. Yeah. And Fermi, for instance, is like a scintillator, like a one square meter scintillator, just doing essentially collecting the the deposition of your gammas into this scintillator and directly measuring the energy.
Now that we were on that, like, I was wondering, so in these wide field instruments that you were mentioning, like it depends on this shower happening with the particles that are present in the air above the detectors, if you wish. So when you're trying to, like, how sensitive is this to the atmospheric conditions of that day or that moment? Like, say, when you want to estimate parameters like, I don't know, energy or something, like how dependent is it on low atmospheric pressure, higher
Yeah,
atmospheric
it's
pressure?
I would say like it's a second order sort of correction. So what we have is models that I mean, in order to sort of fine tune the reconstruction algorithms that we have, there's a program called Corsica that does these false relations. And you can plug the parameters of atmospheric variations of density, atmospheric density. We have done some studies on changing a bit these parameters and seeing how it will impact on the energy. And we see that it's negligible, for instance, compared to miscalibration of these photomultiplier units. Or, for example, there's also the fact that the water starts to get dirty, essentially. So you see less light here. And if you don't characterize it very well, it can be even more impactful than just mismodeling of the atmospheric conditions. Okay. So now that you know how these instruments work, I will go through the GRB detections at very high energies. I will just try to give a very broad overview on these detections and what kind of things we learned from them. The first two happened in 2018 and this other one in early 2019. It was actually like a big thing because Hess detected this GRB, but we kept it secret because we were analyzing the data and it was a big thing and we were like, I mean, we wanted to be very careful of being pretty sure that it was a detection and not something else. And then Magic detected the GRB at the level of 30 sigma. So I mean, 30 sigma is like, yeah, for sure, it's a GRB. We don't need to wait for some confirmation. So they announced it, and then we were submitting the paper, but then the journal Magic told us, no, now you have to wait because we want to do a special issue with all these two detections at the same time. And then so it was very nice because then this was sort of a full recollection of something that was expected for so many years, and all of a sudden there were two detections. So the first was GRB 180720b, and it was actually very surprising because the observation happened at 10 hours after the beginning of the burst. So we were operating the telescope. It was the day in Namibia, and we received an alert that Fermilab had detected a GRB. And then after we got the redshift information from BLT, but it was still the day in Namibia, and we said, okay, this seems to be very interesting because again, the Fermilab detection is not so common, the redshift is not so bad. So we triggered observations with Hess during the night once the GRB was observable. And so we got this detection at the level of 5 sigma at 10 hours after the beginning of the burst. And then after we analyzed the data and we saw the detection, we thought, okay, let's re-observe again a few days later at the 10 days to see if indeed it's a transient event. So, you know, it follows this sort of decay and it's already fainted, you know, so that is no longer detectable. So we got our confirmation. We didn't see anything, which was very nice. I mean, it essentially means it's not a unidentified AGN or some other type of source that went missing in the data. And then it's very interesting when you put it in the context of all the multi-wavelength information. So here you plot again the light source, energy plot as a function of time. For some other instruments, you can see the prompt emission phase here with all these characteristic peaks, and then eventually the onset of the afterglow when everything starts to calm down. And the Hess observation falls at the same level as the X-rays. And we also see, I mean, a hint of very, very uniform decay in the optical with this T⁻² behavior and X-rays. And then, well, the Hertz observation that is similar in terms of flux level. So it was a 5 sigma detection, so it was a bit difficult to pinpoint to any sort of thing regarding the emission mechanism, whether it was synchrotron or synchrotron self-Compton. But all in all, I mean, the energetic requirements here would point again to the fact that the burn-off limit is violated, so probably synchrotron self-Compton could be an alternative. Then there is GRB 1901 for DC, this other GRB detected roughly at the same time, which MAGIC observed during moonlight observations. So that was also very challenging to analyze because for moonlight, then you have to account in your Cherenkov light that there's also contamination due to moonlight, and that's very, very tricky to take into account. But I mean, 50 sigma in 20 minutes, it was an extremely bright observation, and it is a long GRB of T90s of few hundreds, depending on the band where you're observing. It was also a relatively nearby GRB with isotropic energies of the order of 10 to the 53, which is quite big. I mean, standard you get 10 to the 51, 52, 53, 54, 55 is already a lot. And what you see here is the spectral energy distribution. These are XRT observations, Fermilabs, and then MAGIC at different time beings. So in blue is like early afterglow, and then yellow is the second time window of the beginning. And what you can do also is, I mean, not just looking at the data, you can start to do also some modeling. So what you do is you assume that there's a power law distribution of electrons being accelerated, and then they emit gammas that they follow also a power law. The power law will follow an e⁻² distribution with the spectral energy distribution. So in flux is roughly flat. And so this curve here will correspond to the synchrotron contribution to the SED, to the spectral energy distribution. And then here you start to see the modeling that will fit the synchrotron self-Compton part. Here is the data points of MAGIC that correspond to the detected emission, which is attenuated by the EBL. So what you need to do is plug your EBL model and deabsorb your data points in order to get sort of the emitted flux from the source and not the detected one that is attenuated by EBL. So that's something very important because of course it changes a lot the answer that you get from your modeling. So the conclusion here was that synchrotron self-Compton is very well favored by this data, and we can perfectly model this GRB with this assumption. But then, I mean, as a personal opinion, it's not very clear when you see this next energy binning, in which, I mean, the Fermilab spectrum is not well modeled with this synchrotron self-Compton, although they claim that it was. And indeed, again, if you remove this limitation of the burn-off limit of synchrotron, you can actually fit this in with a whole single component that, I mean, it's essentially this synchrotron contribution, but going higher in energy. So to confirm this, we detected a GRB later in that year, so GRB 190829A, that was later published in Science. And as the title says, this thing revealed that there's a very high similarity between X-rays and gamma rays in the afternoon. One thing that I also want to illustrate is how important are these type of observations, because the story was that we started to observe this gamma ray burst at 4 hours after the beginning of the burst, and in CAS and some other ICTs, what we have is a real-time analysis. So it's a system that is directly plugged into the outstream of the data, and we do sort of fast and dirty event reconstruction. in order to instantly get sky maps of the thing that we are observing. With this real-time analysis, we saw that the GRB was present. We were detecting the GRB, and we sent an alert to the other community of optical instruments and radio instruments to perform follow-ups. And there was also some discoveries by SWIFT that essentially SWIFT detected the GRB, but they also saw that there was a galaxy already previously observed that was coincident in space with these gamma ray bursts. And the galaxy was a very nearby galaxy of a redshift of 0.07. So very nearby GRB, which was very interesting, and a lot of instruments follow up on this GRB. So this would be like the ideal scenario for each GRB that we have, that several tens of instruments detect them. In reality, it doesn't happen so often. Sometimes it's just Fermi GBM sending an alert and nobody responds. So this is the light curve of GRB 1908-29A with some other relevant instruments very similar as I presented to 1807-20B. So we see first this detection by heads that is split into 3 nights of observations. So in the first night, we analyze the data offline with all the dedicated analysis methods, and we got this 20 sigma detection that is coincident with this red dot that corresponds to the detection in optical. So opticals have a very good precision. We don't have so much good precision, but we see still the GRB in coincidence. The second observation happened the night after, once we saw that it was fully detected, and we still kept seeing the GRB at 5 sigma, which then sort of broke the record of late time detection at very high energies, because we're talking about delays of 27 hours. And then in the third day, we still see some sort of 3 sigma hint that there's something there, but not well secured. When you do the spectral analysis, which is more sensitive than doing sky maps, you can see still some emission there. So to put things in context, what we saw is for the first time the afterglow decay at very high energy. So we were able to measure the slope of the decay and how the ejecta was slowing down even at very high energies. And we find these very strong similarities between this temporal decay at very high energy, so this line, and the one observed in X-rays. And you see this, the temporal decay index is totally compatible. And so this essentially means that we are talking about a process that is linking the order of 8 orders of magnitude, all of them together, because we are talking of field electron volts of 2 electron volts, photons following the same behavior, also in terms of photon index. So again, the same story. The synchrotron or synchrotron set quantum. We did some modeling there, trying to sort of leave out this synchrotron burn-off limit limitation that you can see here. Here is the SED by X-rays, and here is the test observations. And you can see that the synchrotron, full synchrotron modeling is compatible with what we see in the data, while synchrotron set quantum, it's way difficult to account for the very high energy emission. This is sort of especially solid in this GRB because the redshift was very small. So there is no uncertainty on how big is the absorption in this part due to the ABL. So for sure, this detection looks like this. I mean, the spectral shape is like this. The thing with the synchrotron set quantum not being possible in this case is because you see this temporal decay that is very stable in X-rays and in the very high energy regime. And the problem with the synchrotron set quantum bump is that essentially when your electrons are cooling down, the bump is moving. So of course the spectral shape here will start to get steeper and steeper because the bump is going away. And we don't see that. We see that the spectral shape remains fully constant, several hours in total. So that was sort of the limitation of this this type of theoretical modeling, which is essentially the fact that you assume that you are using one zone in which your electrons and your photons are interacting to do inverse Compton. You can alleviate this thing if you, I mean, yeah, you can talk about, I don't know, hadronic emission or magnetic recognition, shear acceleration, or even the fact, which is something more realistic, that the emission and the acceleration zones are different. There's some people already doing this type of modeling, so calling for something more complicated than what was believed to be operating before, which is now capable of modeling the emission with a pure synchronous Compton component. So the next one to come is the boats. So here it says the boat GRB in context.
You can click OK in that one if you want to take it away.
But the cursor, I don't know how to remove it.
Oh,
It's okay. So the boat is means the brightest of all time, GRB, which is GRB 221009A. And for comparison, this is literally count rates, the amount of photons that were received by Fermi in the interval of the prompt emission phase. You see this GRB, the first that I introduced you, this Fermi-Lab detected 98 gigaelectron-volt photon. The magic GRB and the last one that I was talking about in comparison with this guy. And it was actually so bright that it essentially saturated the satellite. So, I mean, there are some bunches of the data that are not possible to reconstruct because the trigger went crazy and there's no way to recover this data. So it was as bright as that. The isotropic energy release of this guy is 10 to the 55. It's relatively nearby GRB. The other TB detected GRBs were of the order of 10 to the 53, so 2 orders of magnitude brighter. And all in all, I mean, yeah, it's extremely bright, but then if you do the numbers, it's actually has a 10% probability of occurring in between these 50 years since the first discovery of a GRB. So yeah, it's very bright, but sort of expected. And some other curiosities is, for example, that the X-rays and gamma rays from this GRB managed to ionize the Earth's atmosphere, and you see these distortions in the ionosphere of the Earth because of this GRB, which is the first time that something like that is seen. And then yeah, there was a TV detection in the early afterglow by LASSO. So LASSO is one of these wide field instruments, was some sort of the missing puzzle to get a detection not with ICTs, but with wide field instruments, and to prove the fact that they can also do this type of thing. So this is just the field of view of LASSO. So the colors are zenith angles, so yellow means direct overhead, and then blue is more to the horizon. This star is where the GRB happened, and it was essentially in the field of view of LASSO at T0, meaning they could observe the prompt emission, but they didn't observe the prompt emission. They only saw the afterglow, which is something also very interesting in the GRB. And here, for comparison, is the X-ray light curve for a lot of other swift detected GRBs. So this is the whole data of light curves that we have for the rest of GRBs that Swift has observed compared to the GRB. Going, I mean, you know, popping out at 2 orders of magnitude brighter. So if you put this GRB also in context of the isotropic energy release and redshift, some of the TV detected GRBs are around here, and this guy is also going out in this distribution. So it was a very, very bright GRB. It's a long one. It's a long one as well. Yeah.
And there were no to go.
There were a lot of optical follow-ups, radio, X-rays, everything. at late times, early times. There were also estimations by IceCube. If they found neutrinos, they didn't find any neutrinos. So everybody went crazy with this GRB. Yeah. One thing that you can do very easily, I mean, it was so nice the data at very high energies, which is this light curve. You can directly with some Ajecta dynamics equations estimate the initial Lorentz factor of the 600 and the magnetization of 0.3 Gauss. And you see here the spectrum at very high energies, very well behaved in two time intervals. But then the thing that was very intriguing was the fact that LASSO didn't see the prompt emission phase. The GRB didn't emit in the prompt emission at very high energy. You see only here that the afterglow is starting to pop up. So sort of when the ejecta punches out to the circumverse environment, then there's some time in which the photons are accelerating. Some of them manage to escape, and you see this part. And then you see the smooth power law decay, and then the jet break that I was talking about, because of the jetted emission eventually slows down and it goes out of the field of view of the observer. And this temporal evolution of the spectral index. So there's a bit of a big discussion. First, because LASSO published that they had detected a 40 electron volt photon from this gamma ray burst, and people went crazy because they thought that this could only be detected if we were talking about action like particles or Lorentz invariant violation, proton synchrotron, and stuff like this. But something that can be a bit more conservative or realistic is the fact that probably the ABL infrared contribution is underestimated by roughly 40%. So it's the only way that you can explain that the transparency at 10 electron volt photons is less than what has been expected. So this emission and this absorption is well explained with this. So this is a summary of the EV detection so far. The redshift, I didn't talk about 2012-16C because it's a 5 sigma detection. There was no capabilities of extracting more information from this, but it has the record-breaking redshift distance from any source detected at 10 electron volt energy with the redshift. And there are long GRBs, and we also have some things of detection of at the level of 3 sigma and 3.5 from these two GRBs, but that's very a matter of discussion. I will go quickly because I have like 5 minutes still to the future. The future is essentially 2 new instruments that are coming up. One is the Southern Wide-Field Gamma Ray Observatory, and the other one is CTAO that maybe you've heard before from this project. So CTAO is an array or 2 arrays that will be located, one in the south in Paraná, and the other one in the north in La Palma, so very close to where the MAGIC telescopes are already. The south array will have 51 telescopes, all in this sort of configuration, and the big side telescope will be 5. The big ones are the ones that are interesting for GRB observations because are the ones that cover the low energy part. And the north will have a bit less telescopes, and you can later ask me why there's this difference in the number of telescopes in both sides. But all in all, the important thing is that sensitivity will be roughly 1 order of magnitude better compared to current ICT. So MAGIC, Veritas here are in this part. And the estimated sensitivity of CTAO will be an order of magnitude better, but it will also be able to go down in energies as much as 30 dB. You can also see this compared to Fermilab in sensitivity as a function of time, which is more of interest for GRBs. So as I told you before, Fermilab detects of the order of 1 GRB per month. If you have better sensitivity, then there's a big hope that CTAO will detect GRBs more often. And the big thing is LST. So part of this CTAO observatory, there is this sub-collaboration that is building the large size telescopes in the north side in La Palma. So LST is already being built. We have one of these telescopes already working and taking data. And these are photos from yesterday, where we see already the installation of the structure and the mirror structure at the top of one of the LSTs. And the others are also in that path. So yeah, LST1 is very well designed to follow GRBs. The good thing is the threshold at 20 gigaelectron volts, that is very good for the ABL story. And then the pointing is at the order of 20 seconds, so way better than for example, CARES that has the 100 seconds. And already with the data that we are taking with LST, we recently detected this AGN OP313 at a redshift of 0.997, which is like a very good confirmation on the capabilities of these instruments. Regarding GRBs, so we started to observe GRBs since the beginning of operations of LST in 2020, and we have already 30 GRBs observed. Doesn't mean detected because we see only upper limit sometimes. And that's the case for the both GRBs. So this extremely bright GRB, we also observe it with LST. And the only thing is that the first observations happen in moonlight. So this needs a dedicated analysis. But we see very interesting results from this data. And what I'm showing here is the observations at later times where we see only upper limits. But they are very well in context and in agreement with some other observations like Hess and Hoff at similar times. So probably soon we will release the data of the year with the additional observations in the earlier times. And so SWGO, I wanted to talk about SWGO because, well, it's also part of the future, but also because there's a big group here in this bond working on this project. And it's going to be the first wide field of view instrument in the southern hemisphere. The idea would be to place it somewhere here in the south. And currently it's going through consolidation phases. So it's still a project in preparation. It has been decided what will be the configuration of the inner array. And I don't want to talk about this in more detail. And now the time is to decide the site and eventually start to get to the funding agencies and build it. So it will have similar sensitivity than LASSO, but in the southern hemisphere here, LASSO will be here, and then CTA will be also here and here. So there will be, in terms of localization and temporal coverage of GRBs, a very good synergy with SWGO and CTA. And this is my second to last slide about gravitational waves, because this is something that is also happening very fast and very interesting in the VHE regime. So from now, we don't have any sort of coincident detection of very high energy photons in gamma reverse and gravitational waves. The closest thing is GRB 1708-17A, that was this neutron star merger in which we saw electromagnetic counterpart. CARES observed this gamma reverse, but it didn't detect anything. And it is also it's a short GRBs. So we haven't seen any short GRBs of very high energy so far. The thing with gravitational waves is that they are very hard to observe with ICTs, because ICTs have a limited field of view of few degrees, and then the uncertainties of this type of events are more than a few degrees. So if you point to one of these, you cannot cover the whole uncertainty region with only one pointing. So what we do for Cherenkov telescopes is this type of tiny patterns. So this is the localization probability map of an alert like this. And we try to observe the whole localization by pointing at all the different tiles in order to cover it with some limited observations.
That's a Fermi.
Yeah, this is just because Fermi GBM also has very bad capabilities for localizing GRBs, so we also do this type of tiling. But this is the same thing as the gravitational wave case. So we get these alerts with the localization maps, the probability maps, but are like these big blobs, or they sometimes look like a banana, and we have to do tilings to cover this banana pattern.
And but when you get the normal GRB or like or something,
There are,
much more localized.
yeah, exactly. There are few arc minutes or arc seconds depending on who is issuing this. So we just do one pointing and stay there for several hours. Yeah. So again, the advantage of LASSO and Hawk-like instruments is that they see the whole thing. So they are like, if LASSO is standing here, it will see the entire block. And then outside in your data analysis, you can test different positions or wait for an optical instrument to tell you where is it, the GRB, and then you go to your data and analyze it, which for ICTs is not the case. I mean, if you miss it when you're observing it, well, you miss it, and that's the end of the story. So, so I arrived to my conclusions. All these VHC detections were done in long GRBs and during this sort of late prompt or afterglow, but we see that this is full afterglow signatures in all of them. And it seems to be that this is commonly detected in bright and nearby GRBs. So this is again this EISO versus redshift plots. And what is shown here is all these VHC detected GRBs. And also like the LASSO GRB that you see, redshift are relatively small, and they are commonly brighter or low luminosity, but extremely nearby. So this is all because, I mean, ICTs have very good sensitivities, and wide field of view instruments have very high duty cycle. So these two things are complementary, and it's like a balance in between these characteristics. We see also that the TeV emission is closely tracked by the X-ray emission, and this is something that we also explore, because if we know how big is or how bright is the X-ray emission, we can sort of predict how the TeV emission will be, and we use it. We use this observation to optimize our criteria for follow-up of gamma reverse. So the physical interpretation is this CT or synchrotron scenario, but the synchrotron seems to be naturally ruled out because synchrotron quantum is energetically easier, and there are some methods where you can alleviate the discrepancies that you see in the modeling. But then, yeah, I mean, I didn't talk about Lorentz invariance violation action-like particles because then, I mean, it's a different topic, but there are exciting things that can happen with these synergies in very high energies and so on. That's it.
Thank you very much, Edna. Very nice talk, actually. Very illuminating for us that we don't do anything close to this, but we are a bit late, but we have few minutes per question, couple of minutes per question. If someone's got any. Santiago.
So the fact that you don't find any energetic afterwards for sure, where we believe that maybe there is something about the physics and the short and the long run.
Yeah, so I mean, it's hidden in these plots of the redshift distribution of gamma ray bursts. And also another plot that I don't have, lol. Where is the redshift distribution? I mean, the problem is, so the problem is that, so short GRBs are around here. They are more thickly in the one redshift. And long GRBs are more in this. But then, so it means short GRBs are better because they are nearby, so you can detect very high energy. But then also if you plot you can plot the prompt emission versus the afterglow emission for all your sweet detected GRBs, so you get a cloud like this. And actually, short GRBs have around here, meaning the prompt and the afterglow is fainter. And long GRBs are brighter. So, and this is like Yeah, 1 or 2 orders of magnitude difference. So it's a bit again of a competition between it's a short GRB that is nearby but is less brighter.
Yeah, so they're less than it.
Yes.
And do you think you can track that back and forth to central engine? Like one is more powerful? Yes.
I think it's a matter as well of what type of targets do you like particles do you have in the central engine? If there's a lot of availability of electrons and magnetic fields generated in the environment, so it has to do with the environments. Yes.
Or Santiago can be a both. I've got a question, like pushing in the very last comment that you said, like say, so I get that these observations are quite difficult to do, and you need these complementary telescopes or like detectors, but say you start detecting way more with the future instruments, and I get the limitations of the modeling that is done right now with synchrotron and Compton, but you mentioned possibilities for other theories or like something beyond what we know. Like, what is the expectation of like enriching our GRBs observations in terms of like either modeling them, like are we going to see more particle processes? Are we going to constrain our theories better? What's your opinion on that?
I mean, one thing that we would like to understand is if the VHC emission is common. If we can see it in any GRB that we can observe. So far, we know that it happens on nearby and bright GRBs. The moment that we start to get more sensitive at lower energies, it allows us to look further away in distance. And that means that we can test older galaxies because you are looking behind in redshift. And well, there's a question if distant GRBs also need a very high energy that currently we cannot see. And then, well, there's the connection with gravitational waves, neutrinos, Lorentz invariant violation, of course. If detections start to be more sensitive in the time domain, for instance, then Lorentz invariant violation test with GRBs is, I mean, GRBs are like the favorite type of source to do this test of Lorentz invariant violation. But the problem now is that so you do these type of things, like you separate your 20 sigma detection, you separate it in 5 time beams. So it means that this probably is a 5 sigma spectrum. And then with a 5 sigma spectrum, you cannot do a lot of tests on precise type of things because I mean, there's a lot of uncertainty, and some uncertainty you can attribute it to bad reconstruction of your data. The moment that we start to be more sensitive and to have a higher arm in this FTD, so lower energy coverage, then we can start to tell more about the evolution of this time dependent and energy dependent part of the afterglow, and then it's directly easier to do Lorentz violation studies.
If you enjoyed the video, like and subscribe.